Hello my dear friends, in this video we will going to learn about what is the total energy, how much the total energy of a fluid contained when the fluid is flowing. So as we know that in a closed system there must no be there is no any fluid is flowing, that means there is no any mass will enter to the control volume or exit from the control volume. So control mass. So if this is your, let two case, if this is your closed system, that means control mass system, control mass, and there is a control volume, right? So this is called boundary control mass, this is called boundary, and this is called control surface, this is called control surface, right? So as we know that the total energy of a simple compressible system consists of three parts. What is that? Internal energy, kinetic energy, and potential energy, right? We know that the total energy of the system is what? Internal energy, kinetic energy plus potential energy. So on the unit mass basis, E by m is equal to specific internal energy v square by 2 plus gz, this is denoted by small e, right? So this is the energy, this is the total energy of a simple compressible system. That means if you have a simple compressible system, that means a closed system, so this much of energy which is associated with a simple compressible system. But so if there is a heat will in and the work is out, so what is the equation of that? Q minus W is equal to E, right? The delta E, the delta E. So this is for a closed system, this is your heat and mass transfer only, heat and mass, and this is for simple compressible system, simple compressible system, right? But for a closed system, for an open system, but for open system, heat will in, work will out from the system, and also there is a inflow and there is a outflow, right? So for that, because this is open system, so for that the energy, hence when the fluid entering or leaving a control volume poses an additional form of energy, that is flow work nothing, V into V. So this is the difference between the closed system and open system. In a closed system, there are only energy, internal energy, kinetic energy, and potential energy. But when there is an open system, that means there is something in or out. So the energy associated with this system, E, the fluid have internal energy, kinetic energy, and potential energy which is in or which is out. Along with that, there is a flow work, is denoted by theta. So this is work done in pushing the fluid element. Why element? Why? Because we take a property will same pressure, volume, area, element across, always element across the boundary. Hence this is the energy required to maintain the flow in presence of pressure per unit mass, right? So this is the additional work due to flow, right? So what is the energy associated with the control volume? Theta is equal to E plus P into a specific volume, and P into a specific volume. What is theta? U, internal energy, plus kinetic energy, plus potential energy, right? So what is P into U? Enthalpy. So what is that? Energy associated with a control volume, H is equal to H plus kinetic energy plus potential energy. This is the energy associated with the control volume system, right? So using enthalpy instead of internal energy to represent the energy of a flowing fluid. That means if we, in the place of internal energy, we put enthalpy, that enthalpy plus kinetic plus potential energy, that instead of internal energy represent the energy of the flowing fluid. So what you conclude like that, see, if you take non-flowing fluid like that, non-flowing fluid, and there is a flowing fluid, flowing fluid. So what is the energy of a non-flowing fluid? E is what? U plus V square upon 2 plus Gz. And what is the energy of a flowing fluid? E is equal to H plus V square upon 2 plus. This is the energy associated with the system of a flowing and non-flowing fluid. Now see, if this is our a closed system, open system, control volume system, and there is a heat is in per unit time basis and work will out from the system, and there is a, if there is a control volume, so there is a channel here, and this is a control volume, so there is a channel here, right? This is in, and this is your out. So there is a mass into the control volume, and this is your mass out from control volume. So along mass in or mass out, if there is a mass is in, so how much, this is a mass and this is your energy. So if you convert mass into energy, so when the mass will into the system, how much energy will into the system? See how much energy will into the system. So theta into m dot in, and how much mass will out from the control volume? Theta into m dot out. So due to flowing fluid, so due to flowing fluid, theta into m dot be the energy which is transferring with respect to energy which is transferring with respect to control volume system, right? So if there is any control volume, so this much of energy either in or either out from the control volume. So for that, what is the energy now? So by using enthalpy instead of internal energy to represent, if there is enthalpy instead of internal energy to represent the energy of a flowing fluid. So the energy associated with pushing of the fluid or out of the control volume is automatically taken care, right? Why? Because if you write that theta is equal to u plus v square upon 2 plus gz, and also there is a pushing p into v. So p into v is the enthalpy. So if you take theta as enthalpy here, so enthalpy automatically will taken care to the pushing of the fluid. So in fact, this is the main reason for defining the property enthalpy. So this is the very important why the enthalpy will defined. So enthalpy will, so this is why the enthalpy defined. Why? Because by using enthalpy instead of internal energy to represent the energy of the flowing fluid, so the energy associated with pushing the fluid into or out of the control volume is automatically taken care by the enthalpy, right? So what is that? Energy transport by the mass. So if this is your control volume system, and this is your boundary, so what if there is into the control volume, if this is your into the control volume, so there is mass is in, along with the mass, this is your mass is in, this is your kilojoule kg, mass is in kg per second, and along with that there is energy, which is in, this is your kilojoule per kg per mass basis. So how much energy entering to the control volume? M dot I into theta I. So this, the product of, so product m dot I theta I is the energy transported into control volume by, so m dot theta is the energy transport by mass with respect to control volume. This is very important. If the substance is stationary, if the system is stationary, that means what is the amount of energy transport in the form of mass? In the form of mass, what is that? M into theta. That means m h plus v square upon 2 plus gz on the rate basis, A dot mass is equal to m dot theta, and what is that? M dot h plus v square upon 2 plus gz. This is the energy transport, right? When the kinetic and potential energy of the fluid stream are neglected in generally, so energy associated with the mass is what? mh, or energy associated with the mass rate basis, m dot h. So in general, the total energy transported by mass into or out of the control volume is not easy to determine, since the property of the mass at each inlet or exit may be changed with time as well as over the cross section. If we integrate this for the, so what is the energy, total energy into the control volume, energy in the form of mass, what is that? Mass in theta I d m I, what is that? m I h I plus v I square by 2 plus g z I d m I. So this is your energy, total energy which is into the mass, right? This is the total energy. For approximation, what is the assumption in this case? We take number first, steady and one dimensional flow. Number second, one dimensional. Steady and one dimensional flow, right? Thank you very much.